हेलो फ्रेंड, तो राना एकेडमी में आपका स्वागत है। हमने स्टार्ट की 11th क्लास की NCERT वन शॉट सीरीज़, जहाँ पर हमने कुछ चैप्टर्स वन शॉट सीरीज़ में कवर अप किए हैं। आपने वो वीडियो नहीं देखे होंगे तो आप प्लीज़ देख लीजिएगा वो वीडियो, क्योंकि वो बहुत ज़्यादा बेनिफिशियल होंगे आपके रिवीजन में भी। प्लीज़ इस वीडियो को शेयर कीजिएगा ज़्यादा से ज़्यादा फ्रेंड्स तक, क्योंकि आपको रिवीजन में बहुत ज़्यादा बेनिफिट्स होगा वन शॉट सीरीज़ के थ्रू। तो स्टार्ट करते हैं। यूनिट 9 है हमारा हाइड्रोजन। हाइड्रोजन द मोस्ट अबंडेंट एलिमेंट इन द यूनिवर्स and the third most abundant on the surface of the globe is being visualized as the major future source of energy. Hydrogen has the simplest atomic structure among all the elements around us in nature. In atomic form, it consists of only one proton and one electron. However, in chemical form, it exists as a diatomic S2 molecule and is called a dihydrogen. It forms more compounds than any other element. Do you know that the global concern related to energy can be overcome to a great extent by the use of hydrogen as a source of energy? In fact, hydrogen is of great industrial importance, as you will learn in this unit. Position of hydrogen in the periodic table. Hydrogen is the first element in the periodic table. However, its placement in the periodic table has been a subject of discussion in the past. As you know by now that the elements in the periodic table are arranged according to their electronic configurations. Hydrogen has electronic configuration 1s1. On one hand, its electronic configuration is similar to the outer electronic configuration NS1 of alkali metals, which belong to the first group of periodic table. On the other hand, like halogens with the NS2NP5 configuration belonging to the 17th group of the periodic table, it is short by one electron to the corresponding noble gas configuration. Helium NS2 hydrogen therefore has a resemblance to alkali metals, which lose one electron to form a unipositive form of uninegative ion. Like alkali metals, hydrogen forms oxide halide. However, unlike alkali metals, it has a very high ionization enthalpy and does not possess metallic characteristics under normal conditions. In fact, in terms of ionization enthalpy, hydrogen resembles more with halogens. Delta H of lithium is 520 kilojoule per mole. F is 1680 kilojoule per mole, and that of hydrogen is 1312 kilojoule per mole. Like halogens, it forms a diagonal molecule combines with elements to form hydrides and a large number of covalent compounds. However, in terms of reactivity, it is very low as compared to halogens. In spite of the fact that hydrogen to a certain extent resembles both with the alkali metals and hydrogens, it differs from them as well. And now the pertinent question arises as where should it be placed in the periodic table. Loss of the electron from hydrogen results in the nucleus H positive of -1 to 0.5 into 10 to the power -3 pm size. This is extremely small as compared to normal atom and ionic sizes of 50 to 100 pm. As a consequences of hydrogen H positive does not exist freely and is always associated with other atoms and or molecules. Thus, it is unique in behavior and it is therefore best placed separately in the periodic table. Unit 3, dihydrogen H2 occurrence. Dihydrogen is the most abundant element in the universe. 70% of the total mass of the universe and is the principal element in the solar atmosphere. Agent The giant planet of Jupiter and Saturn consists of mostly of hydrogen. However, due to its light nature, it is much less abundant, 0.15% by mass in the Earth's atmosphere. Of course, in the combined form of it constitutes 15.4% of the Earth's crust, and the oceans in the combined form. Besides the and water, it occurs in plant and animal tissues, carbohydrates, proteins, hydrates, and includes hydrocarbons and many other compounds. Isotopes of hydrogen. Hydrogen has three isotopes: protium H1, deuterium H2, tritium H3. T. Can you guess how these isotopes differ from each other? These isotopes differ from one another in respect of the presence of neutrons. Ordinary hydrogen protium has no neutrons. Deuterium, also known as heavy hydrogen, has one, and tritium has two neutrons in the nucleus. In the year 1934, an American scientist, Harold C. Urey, got Nobel Prize for separating hydrogen isotope of mass number 2 by physical methods. The predominant form is protium. Terrestrial hydrogen contains 0.0156% of deuterium, mostly in the form of HD. The deuterium concentration is about 1 atom per 10 to the power of 18 atoms of protium. Of these isotopes, only tritium is radioactive and emits low energy beta negative particles. T is equal to 12.33 years. Since the isotopes have the same electronic configuration, they have almost the same chemical properties. The only difference is in their rates of reactions, mainly due to their different enthalpy of bond dissociation. Table 9.1. However, in physical properties, these isotopes differ considerably due to their large mass differences. Preparation of dihydrogen S2. There are a number of methods of preparing a dihydrogen from metals and metal hydrides. Laboratory preparation of dihydrogen. It is usually prepared by the reaction of granulated zinc with dilute hydrochloric acid. Zinc plus 2 H positive then gives to zinc dipositive plus H2. It can be also be prepared by the reaction of zinc with aqueous alkali. Zinc plus 2 times NaOH then gives Na2ZnO2 plus AOH2 sodium zincate. Commercial production of dihydrogen. The mostly common used processes are outlined below. Electrolysis of acidified water using platinum electrodes given hydrogen 2 times H2O in presence of electrolytes, then give 2 times H2 plus O2. A high purity greater than 99.95% dihydrogen is obtained by electrolysis and form warm aqueous barium dihydrogen solution between nickel electrodes. It is obtained as a byproduct in the manufacture of sodium hydroxide and chlorine by the electrolysis of brine solution. During electrolysis, the reactions that take place on the anode to Cl negative then gives Cl2 plus 2 electrons. At cathode, 2 times H2O plus 2 times electrons then gives H2 plus 2 times OH negative. The overall reaction is 2 times Na positive plus 2 times Cl negative plus 2 times H2O then gives Cl2 plus H2 plus 2 times Na positive plus 2 times OH negative. Reaction of steam of hydrocarbons or coke at high temperatures in the presence of catalyst is hydrogen. The mixture of CO and H2 is called water gas. As this mixture of CO and H2 is used for the synthesis of methanol and the number of hydrocarbons. It is also called a synthesis gas and syngas. Nowadays, syngas is produced from sewage, sawdust, scrap wood, newspapers, etc. The process of producing syngas from coal is called gasification. The production of dihydrogen can be increased by reacting carbon monoxide of syngas mixture with steam in the presence of iron chromate as catalyst. CO plus H2 in presence of 473 Kelvin and then gives in presence of catalyst CO2 plus H2. This is called water gas shift reaction. Carbon dioxide is removed by scrubbing with sodium arsenite solution. Presently, it's minus 77% of the industrial hydrogen is produced from petrochemicals, 18% from the coal, 4% from electrolysis of aqueous solution, and 1% from other sources. The properties of dihydrogen, physical properties. Dihydrogen is a colorless, odorless, tasteless, combustible gas. It is higher, lighter than the air and insoluble in water. Now, its other physical properties, along with those of deuterium, are given in table 9.1. Chemical properties. The chemical behavior of dihydrogen and that matter and molecule is determined to a large extent to bond by bond association, bond dissociation enthalpy. The hydrogen hydrogen bond dissociation enthalpy is the highest for a single bond and between two atoms of any element. What references would you draw from this fact? It is because of this factor that the dissociation of the hydrogen into its atoms is only minus 0.0181%, around 2000 Kelvin, which increases to 95.5% at 5000 Kelvin. Also, it is relatively inert at room temperature due to the hydrogen bond enthalpy. Thus, the atomic hydrogen is produced at the a high temperature is in an electric arc or under ultraviolet radiation, since its orbital is incomplete with one electronic configuration. It does combine with almost all the elements. It accomplishes the reactions by one loss of the only electron to give H positive, gain of an electron to form H negative, and sharing electrons from to form a single covalent bond. The chemistry of dihydrogen can be illustrated by the following reaction with halogens. It reacts with halogens X2 to give hydrogen halides HX, while the reaction with fluorine occurs even in the dark. With iodine, it requires a catalyst. Reaction with the dioxygen, it reacts with dioxygen to form water. The reaction is highly exothermic. Reaction with dinitrogen, it forms ammonia. This is the method of for the manufacture of ammonia by Haber process. Reaction with metals, with many metals has it combines at a high temperature to yield the corresponding hydrates. Section 9.5 H2 plus 2 times M, then gives 2 times MH, where capital M is the alkali metal reactions with metal ions and metal oxides. It reduces some metal ions in aqueous solution, and oxides of metals are less active than iron into corresponding metals. Reactions with the organic compounds, it reacts with many organic compounds in the presence of catalysts to give useful hydrogenated products of commercial importance. For example, the hydrogenation of vegetable oils using nickel as catalyst gives edible fats, margarine, and vanaspati ghee. The hydroformylation of olefins aids aldehydes which further undergo a reduction to give alcohols. Problem 9.1, comment on the electrical reaction of dihydrogen with chlorine, sodium, and copper oxide. Dihydrogen reduces chlorine into the chloride Cl negative ion, and itself gets oxidized to H positive ion by chlorine to form hydrogen chloride. An electron pair is shared between H and Cl, leading to the formation of covalent molecule. Dihydrogen is reduced by sodium to form NaH. An electron is transferred from Na to H, leading to the formation of an ionic compound Na plus H negative. Dihydrogen reduces copper oxide to copper in zero oxidation state, and itself gets oxidized to H2O, which is the covalent molecule uses of dihydrogen. The largest single use of dihydrogen is in the synthesis of ammonia, which is used in the manufacture of nitric acid and nitrogenous fertilizers. Dihydrogen is used in the manufacture of vanaspati fat by the hydrogenation of polyunsaturated vegetable oils like soybean, cotton seeds, etc. It is used in the manufacture of bulk organic chemicals, particularly methanol. CO plus 2 times CH2 in presence of ethanol then gives CH3OH. It is widely used for the manufacture of metal hydrides. It is used for the preparation of hydrogen chloride, a highly useful chemical. In metallurgical processes, it is used to reduce heavy metal oxides to metals. Atomic hydrogen and oxy hydrogen torches find use of for cutting and welding purposes. Atomic hydrogen atoms produced by dissociation of dihydrogen with the help of an electric arc are allowed to combination the surface to be welded to generate the temperature of 4000 Kelvin. It is used as a rocket fuel in space research. Now, dihydrogen is used in fuel cells for generating electrical energy. It has many advantages over the conventional fossil fuels and electric power. It does not produce any pollution and releases a greater energy per unit mass of fuel in comparison to gasoline and other fuels. Hydrogen, dihydrogen under certain reaction conditions combines with almost all elements except noble gases to form binary compounds called hydrides. If E is the symbol of element, then hydride can be expressed as EH2. The example MgH2 and E2H6. For example, B2H6. The hydrides are classified into three categories: ionic or saline, or salt-like hydrides, covalent or molecular hydrides, metallic or non-stoichiometric hydrides, ionic and saline hydrides. These are stoichiometric compounds of hydrogen, dihydrogen formed with most of the S block elements, which are highly electropositive in character. However, significant covalent character is found in the lighter metal hydrides such as lithium LiH, BeH2, and MgH2. In fact, BeH2 and MgH2 are polymeric in structure. The ionic hydrides are crystalline, non-volatile, and non-conducting in solid state. However, their melts conduct electricity and on electrolysis liberate dihydrogen gas at anode, which confirms the existence of H negative ion. Lithium hydride is rather unreactive at moderate temperatures with O2 and Cl2. It is therefore used in the synthesis of other useful hydrides, LiH and plus Al2 Cl6. Now then gives 2 times LiH4 plus 6 times LiCl. Now 2 times LiH plus B2H6 then gives 2 times LiBH4. Covalent and molecular hydrides Dihydrogen forms a molecular compounds with most of the p block elements. Most familiar examples are CH4, NH3, H2O, and HF are convenience hydrogen compounds of non-cometals have also been considered as hydrides. Being covalent, they are volatile compounds. Molecular hydrides are further classified according to the relative numbers of high electrons and bonds in their Lewis structure into electron deficient, electron precise, and electron rich hydrides. An electron deficient hydride, as the name suggests, that has now too few electrons for writing its conventional Lewis structure. A diboron Db2H6 is an example. In fact, all elements in groups 13 will form electron deficient compounds. What do you expect from their behavior? They act as Lewis acid, that is electron acceptors. Electron precise compounds have the required number of electrons to write their group 14 from. Such compounds, example CH4, which are tetrahedral geometry, electron rich hydrides, have excess electrons which are present as lone pairs. Elements of groups 15 to 17 form such compounds. NH3 has one lone pair, H2O two lone pair, and HF three lone pairs. What do you expect from the behavior of such compounds? They will presence of lone pairs on highly electronegative forms like A and O and F in hydrides results in hydrogen bonds formation between the molecules. This leads to the association of molecules. Problem 9.2. Would you expect the hydrides of NO and F to have a lower boiling point than the hydrides of their subsequent group members? Or give reasons on the solution on the basis of molecular masses of NH3, NH2 and HF. Their boiling points are expected to be lower than those of the subsequent group member hydrides. However, due to higher electronegativity of NOF and magnitude of hydrogen bonding in their hydrides will be quite appreciable. Hence, the boiling points NH3H2O and HF will be higher than the hydrides of their subsequent group members. Metallic and non-stoichiometric hydrides. Now, these are formed by meaning D block and F block elements. However, the metals of group 7, 8, and 9 do not form hydride. Even from group 6, only chromium forms CrCH. Now, these hydrides conduct heat and electricity through not as efficiently as their parent metals do. Uh, Unlike saline hydrides, they are almost always non-stoichiometric, being deficient in hydrogen. For example, LaH2, YbH2, TiH2, ZrH2, VH2, NiOH, PDH, etc. In such hydrides, the law of constant composition does not hold to good. Earlier, it was true that in these hydrides, hydrogen occupies interstices in the metal lattice, producing distortion without any change in its type. Consequently, they were termed as interstitial hydrides. However, recent studies have shown that except for hydrides of nickel, palladium, cesium, and Ac, other hydrides of this class have lattice that are different from that of the parent metals. The property of absorption of the hydrogen on transition metals is widely used in catalytic reduction hydrogenation reactions for the preparation of large number of compounds. Some of the metals, PD, BT, etc., can accommodate very large volume of hydrogen and therefore can be used as its storage media. Now, this property has high potential for hydrogen storage and has a source of energy. Problem 9.3 can phosphorus. Now, with the outer electronic configuration 3s2 3p3 form pH5 in the solution. Also, phosphorus exhibits 3 plus 3 plus 5 oxidation states. It cannot form pH5 pH3. Besides some other considerations, high delta H value of hydrogen and delta H value of hydrogen do not favor to exhibit the highest oxidation state of P, and consequently the formation of pH5 water. The major part of all living organisms is made up of water. Human body has about 65% and some plants have as much as 95% water. It is a crucial compound for the survival of all life forms. It is solvent of great importance. The distribution of water over the earth's surface is for not uniform. The estimated world water supply is given in table 9.2. Estimated world water supply. Source oceans 97%, saline lakes and island seas 0.08, polar ice and glaciers 2.04, groundwater 0.61, lakes 0.009, soil moisture 0.005, atmospheric water vapor 0.001, rivers 0.001. Physical properties of water. It is a colorless and tasteless liquid. Its physical properties are given in table 9.3 along with the physical properties of heavy water. The unusual properties of water in the considered condensed phase, liquid and solid states the are due to the presence of extensive hydrogen bonding between water molecules. This leads to high freezing point, high boiling point, high heat of vaporization, and high heat of fusion. In comparison of H2S and H2SE, in comparison of to other solid liquids, water has a higher specific heat, thermal conductivity, surface tension, dipole moment, and dielectric constant, etc. These properties allow water to play a key role in the in biosphere. Molecular mass, melting point, boiling point, enthalpy of formation, enthalpy of vaporization, enthalpy of fusion, temperature of maximum density, viscosity, dielectric constant, electrical conductivity. The high heat of vaporization and heat capacity are responsible for moderation of the climate and body temperature of living beings. It is an excellent solvent for transportation of ions and molecules required for plant and animal metabolism. Due to hydrogen bonding with polar molecules, even covalent compounds like alcohol and carbohydrate dissolve in water. Structure of water. In a gas phase, water is a bent molecule with a bond angle of 104 degree, and OH bond length is 95.7 pm as shown in figure 9.1. It is highly polar molecule. Its orbital overlap picture is shown in figure 9.1c. In the liquid phase, water molecules are associated together by hydrogen bonds. The crystalline form of water is ice. At atmospheric pressure, ice crystallizes in the hexagonal form, but at very low temperatures, it condenses to cubic form. Density of ice is floats on water in winter season. The ice formed on the surface of lake provides thermal insulation, which ensures the survival of aquatic life. This fact is of great ecological significance. Structure of ice. Ice has a highly ordered three-dimensional hydrogen bonded structure as shown in figure 9.2 examination of ice crystals with X-rays have shown that each oxygen atom is surrounded tetrahedrally by two four other oxygen atoms at a distance of 276 pm. Hydrogen bonding gives ice as a rather open type of structure with the wide holes. These holes can hold some other molecules of appropriate size interstitially. Chemical properties of water: amphoteric nature, redox reaction involving water, hydrolysis reaction, hydrates formation, hard and soft water, temporary hardness, permanent hardness. Temporary hardness, boiling Clark's method; permanent hardness, treatment with washing soda, carbo, sodium carbonate, Calgon's method, ion exchange method, synthetic resins method, hydrogen peroxide preparation. Physical properties, chemical properties, structure, storage, uses: heavy water D2O, dihydrogen as a fuel, amount in this view, hydrogen economy is an alternative. The basic principle of hydrogen economy is the transportation and storage of energy in the form of liquid or gases. The hydrogen advantage hydrogen economy is that energy is transmitted in the form of dihydrogen and not as electric power. It is for the first time in the history of India that a pilot project using dihydrogen as a fuel was launched initially in October 2005 for running automobiles. Initially, 5% dihydrogen has been mixed in CNG for use of in four-wheeler vehicles. The percentage of dihydrogen would be gradually increased to reach the optimum level. Nowadays, it is also used in fuel cells for home generation of electric power. It is expected that economically viable and safe sources of dihydrogen will be identified in the years to come for its uses as a common source of energy. Table 9.5: energy released by combustion of various fuels in moles, mass and volume. Then summary देखते हैं. Hydrogen is the highest atom with only one electron. Loss of this electron results in an elementary particle, the proton. Thus it is unique in character. Now it has three isotopes, namely protium, deuterium, and tritium. Almost amongst these three, only tritium is radioactive, in spite to its resemblance both with alkali metals and halogens. It occupies a separate position of the periodic table because of its unique properties. Hydrogen is the most abundant element in the universe. Now, in the free state, only it is almost not found in the Earth's atmosphere. However, in the combined state, it is the third most abundant element on the Earth's surface. The hydrogen on the industrial scale is prepared by the water gas shift reaction from petrochemicals. Now it is obtained as a byproduct of by the electrolysis of brine. The hydrogen bond dissociation enthalpy of dihydrogen 435.88 kJ per mole is the highest for a single bond between the two atoms of any elements. This property is made use of in the atomic hydrogen torch, which generates a temperature of minus 4000 Kelvin and is ideal for welding of high melting metals. Through dihydrogen is rather inactive at room temperature because of very high negative dissociation enthalpy. It combines with almost all the elements under appropriate conditions to form hydrides. All the type of hydrides can be classified into three categories: ionic and saline hydrides, covalent and molecular hydrides, and metallic and non-stoichiometric hydrides. Alkali metals hydrides are good reagent for preparing other hydride compounds. Molecular hydrides example B2H6, CH4, CnH3, H2O, are of great importance in day-to-day life. Metallic hydrides are useful for ultra purification of dihydrogen and as dihydrogen storage media among the other chemical reactions of dihydrogen, reducing reactions leading to the formation of hydrogen halides of water, ammonia, methanol, vanaspati ghee, etc. are of great importance in methanol in metallurgical processes. It is used to reduce metal oxide. Now, in space programs, it is used as a rocket fuel. In fact, it has promising potential for use as a non-polluting fuel of the near future hydrogen economy. Water is the most common and abundantly available substance. It is of a great chemical and biological significance in his with which water is transformed from a liquid to solid and to gaseous state allows it to play a vital role in a biosphere. The hydrogen burning, which is the maximum in ice and least in water vapor, the nature of water makes it a very good solvent for ionic and partially ionic compounds. Different types of its property to us dissolve many salts, particularly in large quantity, makes it hard and hazardous for industrial use. Both temporarily and permanent hardness can be removed away by the use of zeolites and synthetic ion exchangers. Heavy water D2O is another important compound which is manufactured by the electrolytic enrichment of normal water. It is now essentially used as a moderator in the nuclear reactor. Hydrogen peroxide H2O2 has an interesting non-polar structure and is widely used as an industrial bleach and is the in pharmaceutical the pollution control treatment in industrial and domestic effluents. तो यहाँ पर हमने हाइड्रोजन वन शॉट सीरीज में स्टार्ट किया था। हाइड्रोजन चैप्टर 9 यूनिट है। से 11th क्लास की केमिस्ट्री स्टार्ट की थी हमने, जहाँ पर हमने हाइड्रोजन चैप्टर वन शॉट सीरीज में कंप्लीट किया है। तो हमने पहले से देखेंगे क्या क्या हमने देखा। पोजीशन ऑफ हाइड्रोजन इन द पीरियोडिक टेबल, देन डाइहाइड्रोजन देखा, आइसोटॉप्स ऑफ हाइड्रोजन देखा, देन प्रिपरेशन ऑफ डाइहाइड्रोजन देखा, लैबोरेटरी प्रिपरेशन ऑफ डाइहाइड्रोजन, कमर्शियल प्रोडक्ट ऑफ डाइहाइड्रोजन, properties of dihydrogen, physical properties, chemical properties, then uses of dihydrogen, then dihydrides, then ionic and saline hydrides, then covalent and molecular hydrides, देन उसके बाद हमने देखा मेटेलिक एंड नॉन स्टोइकोमेट्रिक हाइड्रेट्स, देन उसके बाद वाटर देखा, फिजिकल प्रॉपर्टीज ऑफ वाटर, स्ट्रक्चर ऑफ वाटर, देन स्ट्रक्चर ऑफ आइस, then chemical properties of water, then hard and soft water, then temporary hardness, boiling Clark's method, permanent hardness, treatment with washing soda, Calgon's method, ion exchange method, synthetic resins method, hydrogen peroxide preparation, physical properties, structure, chemical properties, storage, uses, heavy water, D2O, dihydrogen as a fuel, then summary। तो ये सब हमने हाइड्रोजन चैप्टर में देखा, जहाँ पर हमने वन शॉट सीरीज में हाइड्रोजन चैप्टर को कवर अप किया है। प्लीज़ इस वीडियो को ज़्यादा से ज़्यादा लोगों तक शेयर कीजिएगा। प्लीज़ लाइक शेयर एंड सब्सक्राइब। थैंक यू सो मच फॉर वॉचिंग।